gasoline, selecting the groups of molecules wanted and changing their sizes and shapes as required. To do this job calls for great storage tanks to maintain a constant supply of crude oil. Batteries of pumps. A maze of valves and pipes. Mighty facilities. And an army of experienced, specially trained workers. The first step is to separate the crude oil into the parts that you saw a moment ago. This is done by distillation. You know that when you boil water, the vapors can be condensed. The same principle is used in distilling crude oil. Giant units with bubble towers condense vapors just as the cold tumbler did. Here in a single tower, much simplified, crude oil is separated into the different fractions needed for gasoline, kerosene, fuel oil, and other petroleum products. Here we see the crude oil being heated. Most of it is vaporized. At the bottom of the bubble tower, unvaporized large molecules of heavy lube oil and residual materials are drawn off. At the second level, the light lube oil is condensed out of the vapor and withdrawn. At the third level, the largest of the lighter remaining molecules condensed to form the fuel oil cut. At the fourth level, kerosene is condensed and drawn off. At the fifth level, the gasoline molecules become liquid, leaving the very light gas molecules to go out the top of the bubble tower. In the average crude oil, only a limited amount of gasoline is present. So let's see what we might get from this simple distillation. A barrel of crude oil produces 20% residual fuel oil and asphalt, 7% lube oil and wax, 39% gas oil and fuel oil, 15% kerosene, 1% gas, and gasoline only 18%. Not nearly enough for today's millions of cars. But scientists of the Standard Oil Company, Indiana, invented the cracking process, enabling refiners to make more than twice as much gasoline from each barrel of crude. Today, were it not for the demands for fuel oil and diesel fuel, almost the whole barrel could be converted into gasoline. By making more gasoline, cracking has conserved our natural resources and at the same time made gasolines of higher anti-knock quality for greater performance and economy. Here's a typical gas oil molecule to be cracked. You are already familiar with the way it's constructed. To crack it, heat is applied under precisely controlled conditions. More heat than is needed for distillation. And now, folks, you are watching science change a molecule into more useful ones. On the left are two gasoline molecules. On the right are gas and carbon, all obtained from cracking one gas oil molecule. Thus, science creates gasoline where none existed before, high anti-knock gasoline. Here are some of the great units that do the cracking. And here's one that cracks tens of thousands of barrels of gas oil each day. Standard's continuing leadership was also strengthened by other processes. One is called polymerization. It simply takes molecules that are too small for gasoline, such as these gas molecules, unites them by the polymerization process to form a larger molecule, a gasoline molecule of exceptionally high anti-knock value. Thus, science again fashions for us more and better products. By a somewhat different process, this alkylation unit joins together two different molecules to make another high-octane gasoline component. And this unit, a hydroformer, changes the shape of molecules and takes out some of their hydrogen to make still more high antinocq material. Finally, a process where cracking is affected by a catalyst, a reaction promoter that itself remains unchanged. The most modern method uses catalysts in a fine powder that will flow like a fluid. Here's what happens inside a fluid catalytic cracker. Gas oil is heated. It is joined by the hot, finely powdered catalyst shown here as little white grains. The hot oil and the still hotter catalyst then move together through pipes up into a chamber called the reactor and are tumbled about. Here the heavy oil molecules are cracked by catalytic action to produce gasoline molecules shown in red. These move out at the top. As the catalyst becomes covered with coke, it becomes less active and is drawn off at the bottom. Air blows it through a pipe to the regenerator, where the coke is burned off. This reheats the catalyst, which again joins the flow of incoming oil. Here's the entire operation showing the complete cycle. Notice that the same catalyst is used over and over again in this, the most modern method of gasoline manufacture. It takes a complicated unit to do the job. Every 2 minutes, a whole carload of catalyst passes through the lines. 16 stories high, each of the company's big cat crackers can produce enough gasoline in one day to last the average motorist 1,000 years. Contrast the modern unit you have just seen with this historic Burton cracking still at Whiting, Indiana, the first successful commercial cracking unit. Though the amount of oil in today's catalytic cracking units is actually less than in the old Burton units, the catalyst cracks the gas oil more than 7,000 times faster, and so permits much greater throughput. It is one more demonstration of leadership through science. To build top gasoline performance today, there are two major requirements: proper volatility and proper antinocq quality. Let's take the first one, volatility, the tendency to change from liquid to vapor. The driver may not know a cat cracker from a firecracker, but he knows when his engine starts. And he wants it to warm up without coughing and sputtering. But starting and warm-up are not the whole story. In all seasons, the motorist wants quick acceleration. He wants economy, too. Mileage. And that calls for a scientific balance of gasoline components. You know how easy it is to ignite gas, which is made up of small molecules. Here's a mixture of liquid hydrocarbons so light and volatile that the heat of a hand will make it boil. It's inflammable and so volatile it ignites plenty fast. Now here are some of the heavier, less volatile hydrocarbons. The lighted taper does not ignite them, yet when vaporized and burned in an engine, they pack a lot of power and give mileage. To make a gasoline blend that will have a proper combination of volatility characteristics, first we put in the very light hydrocarbons for quick starting. The next heavier ones have rapid warm-up. Then some that give instant acceleration, and the final portion for full power and good mileage. The blended gasoline has the desired range of performance with economy because it contains just the right groups of hydrocarbon molecules. One, for instance, starting, but so active that in the summer he should be used only in moderation. One for rapid warm-up. one for smooth acceleration, and one for full power and good mileage. Molecules that work together, a harmonious team. In the engine laboratory, by means of a glass intake manifold, you can actually see one of the volatility differences between fuels. Slowing down the action, here's what too low volatility causes: a wet manifold and imperfect distribution. These liquid droplets decrease engine performance, waste mileage, and dilute the crankcase oil. Switching to a fuel with proper volatility, vaporization is complete and there's no waste. To assure trouble-free performance at all times, fuels are tested out on the road as well as in the laboratory, in all types of engines and under all of the different seasonal and climatic conditions of use. Under city driving and trip conditions in hot weather and cold. Seasonal variations and the climates of different regions must be taken into account. That is why the Standard Oil Company, Indiana, adjusts volatility to suit the season and the region in which its gasolines will be used. A distillation test measures the volatility of motor gasoline. The results here plotted form a typical distillation curve for a gasoline of proper volatility. Now for the next major requirement, the prevention of fuel knock.
The motorist wants smooth, controlled application of power. Using a special demonstrator, I shall show the difference between poor performance and good performance. Now, with the hard face of this mallet, I strike the piston. The piston, you see, receives a punishing rap, showing how power is wasted when gasoline knocks. This time, I shall use the cushion face of the mallet to show what happens when gasoline does not knock. Smooth, useful power propels the piston, sends the crank spinning. The performance difference you've seen is a mighty important one that you ought to understand better. So let's look inside the engine by means of animation and see what happens when the fuel burns. These gasoline molecules have not been improved on or controlled by science. They are untamed and unruly. What you will see next actually takes place in about 1/500th of a second. First, the spark ignites the compressed fuel charge. Now, watch for the knock. In this greatly slowed down action, you could see that with this gasoline, combustion was uneven and uncontrolled, and at the end there was a jarring, violent explosion, a knock that pounded and shook the engine. Now we shall repeat the action. Watch again for the knock. Now, with gasoline made up of molecules that have been science-fashioned so that they have the required anti-knock quality, molecules that stay under control and work as a team, let's see what happens. Note in this case that the combustion is more uniform and there is no knock. The big difference, as you could see, is that with gasoline of the required anti-knock quality, there is no knock. Combustion is smooth and even and completely under control. Now we shall repeat the action. Watch how the combustion proceeds as it should, smoothly and without the interference caused by knocking. In the modern high-compression engine, modern gasoline gives the greater performance required today. The car accelerates more rapidly, climbs hills faster, travels more miles per gallon. In addition to fashioning the molecules to prevent fuel knock, Refineries usually add minute quantities of tetraethyl lead to help accomplish the same purpose. This model shows how just the right amount of fluid containing tetraethyl lead and dye is added to the gasoline. In the knock testing laboratories, test engines are used to make sure that the proper anti-knock quality has been built into Standard Oil's gasolines. The high anti-knock reference fuel is called isooctane, hence the expression octane number. This test engine is equipped with a dial indicator that shows just how badly the engine is knocking. With a fuel of low octane number, here's how it sounds. Switching to a high octane number fuel, the knocking diminishes and finally fades out completely. This illustrates the smooth, even performance you get from Standard Red Crown and Standard White Crown.
The engineer has had his say, but modern processes and skillful know-how are not enough. There must also be safeguards. You can depend on it that Standard Oil Company, Indiana, constantly checks and inspects its fuels by every needed control test. For example, the vapor pressure test that controls vapor lock tendencies. A test to make sure there is no harmful gum. Another to make sure that today's fine gasolines will not deteriorate in storage. A test that guards against corrosive impurities. Testing, testing, testing. Another of the 1,500 and more daily control tests. In addition, these great laboratories are entirely devoted to extensive research. Carried on by hundreds of capable scientists, working on more and still better products for the future. Cooperative work with the automobile industry guarantees that the right gasoline will always be available for any car that's developed. Put all of this together and you have what it takes to deliver today's and tomorrow's great motor fuels. Huge units like this super fractionator and the other multi-million-dollar units that go to make up the great modern refineries of the Standard Oil Company, Indiana. With the tradition of pioneers behind us and better facilities ahead of us, future progress leading to still finer products is assured. So there's the story, folks. I'm proud to be a part of it, even if only as a tiny atom inside modern gasoline. This is what's behind the gasoline you sell, whether from tank truck or on the service station driveway. Behind these symbols of service is a great record of scientific achievement that certifies today's leadership and guarantees tomorrow's.